Now in this lecture we will look at one of the most important method for the preparation of ethers, right, which is Williamson synthesis. In Williamson synthesis we treat sodium alkoxide with alkyl halide, right, to get ethers, right. Let's look at the reaction. We take, this is your sodium alkoxide, this is treated with alkyl halide, right, to form, this is your, you can just do this, sodium halide. Sodium halide would be removed. We need RO. This RO would be coming from sodium alkoxide, right, and this the other alkyl group of ether would be coming from the alkyl halide, right, plus your NaX, right. This is your Williamson synthesis for the preparation of ethers, right. Now the important thing that you need to look is, from using this method you can prepare simple alcohols and mixed alcohol, you can prepare simple ethers and mixed ethers. Mixed ethers where you have different alkyl groups, right. So now this method is best used when alkyl halide used is primary alkyl halide, right. Alkyl halide is your primary alkyl halide, right. And if I use secondary or tertiary alkyl halide, then the product that I will get is your alkene. Instead of ether I will get an alkene, right. In case of secondary halides, if I take secondary halides, I get mixture of alkenes and ethers, right. And if I take tertiary halides, then I will get your alkenes, right. I will not get ethers. I will get ethers but very less, right. The reason is that the tertiary halides, right, we know tertiary halides are where your carbon atom is connected to 3 other carbon atoms directly, right, like this. Here your carbon atom, this is your tertiary carbon atom which is connected to 3 other carbon atoms. So if I take this type of halide in Williamson synthesis, what I will get is an alkene and not an ether, right. In case of secondary I'll get a mixture. In case of primary I'll get ethers, right. Alkyl halide is ether. Now the reason that I get alkenes, right, with tertiary halide is that these tertiary halides these tertiary halides undergo dehydrohalogenation very easily, right. If you remember, we have done this in the previous lecture where we studied regarding the dehydrohalogenation of alkyl halides, and we found that the tertiary halides, right, can easily undergo dehydrohalogenation, right, followed by secondary, then your primary, right. Why? Because if you remember, if this is your tertiary halide, right, all these methyl groups are electron releasing, right, and this electron pair between CX bond, right, this electron pair between CX bond is already more towards your halogen atom, because your halogen atom is electronegative, more electronegative than carbon. So when you have high electron density on this carbon atom, right, because of these 3 methyl groups, this electron pair would be, since it is negative, right, since it has more negative charge due to these electron releasing groups, so it will repel this electron pair more towards your X group, towards halide, right, and it will easily leave, right, this will easily leave, right, this will easily leave to form, this is the kind of product that CH2, right, this is the product that you will get, right, because tertiary halides are more prone to dehydrohalogenation, it will not give you ethers, so that is why we prefer to take primary halides, right, because primary halides will give you ethers, majorly ethers in Williamson synthesis. Now suppose, okay, first let's see some of the reactions. Suppose I have taken sodium methoxide, right, and I treated with methyl chloride. The compound that I will get is CH3OCH3 plus NaCl, right, this is your simple ether. Now if I take CH3ONa plus your C2H5Cl, then the product that I will get is CH3OC2H5, right, this is your ethyl methyl ether, common name, right, or methoxyether. This is your mixed ether, this is your simple ether, right, and this alkoxide that you have in this Williams synthesis, you can obtain it by treating alcohol with sodium hydroxide, where you get sodium methoxide plus water, right. Now suppose if I want to obtain, suppose if I want CH3, right, O, then you have say C2H5. If I want this type of ether, right, where you have this tertiary butyl group, right, this is your tertiary butyl, right, and this is your ethyl group, right, and this is your ethereal oxygen. So this is basically an ether. So Williamson synthesis, in Williamson synthesis, if you look, one R is coming from alkoxide, the other R is coming from alkyl halide, right, but we said that if I take, suppose this alkyl halide, to get this alkyl halide, if I take this, if I take a tertiary halide, then as per this what we have learnt, what I will get is an alkene, right, but in this, if you look at this general reaction, RONA plus RX, this is how we will obtain it. So if I take R as tertiary butyl, right, this will be CH3X plus, say this is CH3ONa, right, then what would be the product in this case, like what product will I get? The product that I will get is, as per this, I will get an alkene, CH3 double bond CH2, right, CH3OH plus NaX, this is what I will get, right. If I use tertiary halide, I will not get this. Now suppose if I want this compound, then this tertiary butyl should be with sodium alkoxide, it should not be with alkyl halide, because if I keep tertiary halide, this tertiary butyl with this alkyl halide, what I will get is an alkene, like we did here, right. But to get this compound, what reactants I will take is, you will take CH3ONa, sodium tertiary butoxide, sodium tertiary oxide, right? So this would be treated with CH3Cl. This is your primary halide, and we said that with primary halide we will get always ethers, right? So here the product would be, or since I said that we want this compound, then instead of CH3 you can take C2H5, right? This is also a primary halide, CH3, CH3, CH3O, C2H5. This is how we will obtain it, right? So this is, first just understand that this Williamson synthesis. Now let's look at the mechanism, right? Williamson synthesis, this is your nucleophilic substitution reaction, right? Nucleophilic substitution, and this is your SN2 reaction, right? Where this nucleophile will attack this alkyl halide, right? And this will go through a tertiary state. This will go through a transition state, right? Where you have this also, where you have this nucleophile connected to this carbon of the methyl group, and you have this Cl also connected to the methyl group in that state. It would look like this somewhat. If we are considering this reaction, then it will look like it would be, suppose this is your methyl, right? Then what I will get here is again methyl, right? Now how this reaction will take place? When this nucleophile will attack the carbon of this alkyl halide. Right. So this is your transition state, if you remember, in SN2 reactions. So this bond is in process of making, and this bond is in process of breaking. Right? This bond is in process of making, and this bond is in process of making. Right? This is your SN2 mechanism. Now, this is a strong base. Right? This tertiary butyl oxide, this is a strong base. Right? So it will replace this, right, and will form this compound. So this is your nucleophilic substitution reaction, SN2 reaction, where this oxide, right, this alpha oxide, tertiary butyl oxide, would be your nucleophile, and it will attack the carbon of the alkyl halide to form the transition state, right, where one bond would be making and other would be breaking, right. So this will break to form this compound, right. Now what we said, that tertiary halides, if used, will give you alkenes. This is one of the major limitations, right? This is one of the limitations of this reaction, right? This is the limitation, that tertiary halide cannot be used. Tertiary halide cannot be used, since it gives alkene as the product and not an ether, right? So this is one of the major limitations of the reaction, that tertiary halide cannot be used, right? And suppose if I now want to prepare an ether, say if I want to prepare this ether, right? Now this is your phenyl methyl ether, right? Phenyl methyl. Sorry, this is your methyl. M comes first, MnOP methyl phenyl ether. So how will you prepare this? From where this phenyl will come, this will come, and from where this R will come, the other methyl. Right? In this case, the reactants that we will use is plus your primary halide, which is your, say, this is the product. Now important thing to consider here is, suppose I take this phenyl bromide plus CH3ONA. If I take this, then this reaction will not take place. No ether, you will not get any ether. If you take aryl bromide, phenyl bromide with phenyl bromide, the reaction will not take place. Why? Because if you remember, we have done this in haloalkanes and haloarenes, that this bond, right, this one, since it has lone pair, right, it will enter, this lone pair will enter into benzene ring, right, and it will enter into delocalization with the benzene ring. This lone pair of electron on the halide ion will enter into delocalization with the delocalized pi system of the benzene ring, or simply it enters into the benzene ring, forming, what it will form is this. It will form a double bond between carbon and halogen atom, right? We have a resonance structures that we have done before. You can check the previous lecture where we studied the comparison of reactivity between alkyl halides and aryl halides, right? So here it develops due to this delocalization, right, of lone pair of electron on this halogen atom. It develops a partial double bond character, and we know that double bond is stronger bond as compared to the single bonds, right? If I compare it with this, right, it has a single bond with carbon, right? This compound, it has a pure single bond with carbon, which is easy to break. But if I take aryl bromide, it is difficult to break aryl bromide because it, due to resonance of this lone pair of electrons, it will develop a partial double bond character, which is a strong bond. So it is not possible to replace this halide ion, right, from here by this nucleophile, by this methoxide nucleophile. So that is why this reaction won't take place and you will not get this ether. In order to get this ether, the phenyl should be, this phenyl group will come from sodium phenoxide, right, not from phenyl bromide. Just understand this concept, right? I hope all this is clear. This is very important reaction. Thanks.